Good evening students, and now I am going to present the topic as electromagnetic waves. We know very well electromagnetic waves are constituted by periodic variation of electric field as well as the magnetic field. These two fields are separate yet they are closely related to each other. This wave propagates in such a way that electric and magnetic fields are perpendicular to each other, and also electromagnetic wave is perpendicular to the direction of propagation of waves, so that electromagnetic waves are transverse in nature. In figure shows the electric field and magnetic field is perpendicular to each other. We know very well in sound waves or water waves, waves in stretched strings, particles will move, but in whereas in electromagnetic waves, particles will not move because the intensities will change in electromagnetic waves. The figure shows the movement of the electromagnetic waves. Here particles will not move, intensity of the wave only change. Maxwell predict the electromagnetic waves or propagates in free space or vacuum, means with a speed of free space or vacuum with the velocity of light. So Maxwell only explain the electromagnetic waves and their properties and applications. Formulations or formulated of Maxwell's equations are, there are four Maxwell's equations. Equation 1 is del dot D vector is equal to rho. D vector is a displacement current, rho is charge density. And second Maxwell's equation is del dot B vector is equal to 0. B vector is magnetic field or magnetic flux. Third equation is del cross E vector is equal to minus dou B vector by dou T. B vector is magnetic field. Fourth equation is del cross H vector equal to J plus dou D by dou T. J is the current density, D is the displacement, H is a magnetic field intensity. We will see how to derive the Maxwell's equations. First one, Maxwell field equation from Gauss electric law. Gauss law means we know very well the closed integral of electric field intensity is equal to 1 by epsilon naught times of total charge. According to Gauss law, the electric field can be right surface integral of E vector dot ds equal to q by epsilon naught. This equation is again written as epsilon naught is multiplied this side, so epsilon naught E vector dot ds equal to total charge q. We know very well displacement current D vector equal to epsilon E. Epsilon is permittivity of the medium. Permittivity epsilon is equal to epsilon naught epsilon r. We can write so that D vector epsilon E can be replaced to epsilon naught into epsilon re. We are choosing the medium is air. Medium is air is perfectly dielectric medium, so epsilon r is equal to 1. D vector is equal to epsilon r is equal to 1 means remaining D vector is equal to epsilon naught into E vector, so that equation 2 written as equation 1 is written as epsilon naught E can be replaced to D vector. So surface integral of D vector dot ds is equal to q. We know very well the total charge q is equal to charge density rho over the volume v, so that q which is equal to volume integral of rho dv. So substituting, comparing equation 3 and 4, we get the answer surface integral of d vector dot ds is equal to volume integral of rho dv. So equation 5 represents the Maxwell's first equation in integral form. We need to find the Maxwell differential equation. By using Gauss divergence theorem, surface integral can be converted to volume integral or volume integral converted to surface integral. We know closed integral of surface integral of d dot ds is equal to volume integral of, here taking divergence, so here the d vector is a vector quantity, so del dot d vector is equal to dv. So finally we can write d dot ds equal to del dot d into dv. So q is equal to, interchanging this equation, del dot d vector dv equal to rho dv. So volume integrals are equal. So integrals are equal means finally equation 7 become del dot d vector is equal to rho. So Maxwell's first equation, this is the del dot d vector equal to rho is Maxwell's first equation in differential form. Thank you.